All right, so this is the XFLR5 individual project. I'm going to be just going through the details of this project and then showing how to do it in XFLR5 real quick. So obviously there are some plots that we need to get. We need to get CL versus alpha, CL over CD versus alpha, and CL over CD. We're all dealing with the Clark-Y airfoil, but we're doing not only the airfoil, but also wings with the airfoil at different aspect ratios. So we're going to go through that and how to get the plots for that. And then all of these values that we need to get and some that we need to calculate after we get some of the important values from there. So I'm going to go ahead and open up XFLR5 and share that so we can get started. Okay, so you should be able to see my XFLR5 window now. Obviously, it just comes up with a blank screen to start. So the first thing we're going to need to do is we're going to open up our direct foil design, and you should get this screen. And what we need to do is we need to open our Clark-Y data file. So our Clark-Y file is similar to all the other files that we've had. I can actually open that up and show what that looks like just in a notepad. Let me share that screen really quick. So if I open up my Clark-Y airfoil, the data sheet that we get from the UIUC website, if you download the zip file off of that website, you can get the file where the coordinates are already arranged correctly. Just to reiterate, to have them arranged correctly, you need to have, you start from the trailing edge, you go up over the top surface of the airfoil. So you can see it goes from the trailing edge toward the leading edge in X, and the Y coordinates are positive. So again, you're doing the upper surface, and then it goes, you get to the the leading edge where X is 0, and then you go back down the lower surface, back down to the trailing edge from there. So this is what your file should look like. Like I said, if you open up the zip file with all the different airfoils in it, this is the file you'll already get naturally, which is really nice. So just make sure you do that and you'll have the right file that you need for XFoil or for XFLR5 and XFoil, either one, to read it properly. So to load this one in here, we're going to go ahead and go to open, and then I'm just going to go ahead and click that same Clark-Y file that I had. We hit open and it pops right up. So it's loaded in correctly. And I know just because I've done it before, but obviously you'll want to make sure that the points converge. But this is what it should look like. We can obviously get different airfoils in there. We could get like our NACA airfoils, but we don't need to do that for this project. We are just dealing with the Clark-Y airfoil. So you can have multiple of them loaded in here, which is really nice. And it gives you all the data about them as well, which is super useful when you don't have like a NACA foil that you already know all the data from the NACA foil number. So with this loaded in here, we can go to our XFoil direct analysis, which is built into XFLR5. Super, super nice. You can see it already is doing it for the Clark-Y airfoil since that's the only one we've loaded in. So in order to get any data for the airfoil, what we're going to need to do is define an analysis. So we come up to analysis and define an analysis. And we're just going to do type 1. That's going to be one where we can just modify the Reynolds number and Mach number. We're not going to worry about Mach number here, but we are going to modify our Reynolds number. So for this project, it's 1 million. So that's what we're going to do. And everything else is defined just fine. So we'll go ahead and hit OK. And it pulls this up, and you can see now this direct foil analysis screen was grayed out before. But once we've defined our analysis, we are ready to prepare that. So for the project, what we need to do is an alpha sequence. So we're getting data points at each varying alpha value, so angle of attack value. And I've already got the sequence loaded in here properly, but basically what we're trying to do is we're going from -5 degrees to 20 degrees with a change of 1 degree, a step of 1 degree on each one. So we'll get -5, -4, -3, and so on all the way up to 20. We want viscous on. Everything else is set the way we want it, so we can go ahead and hit analyze. And look at that, it generates all the graphs for us real quick, real easy. We've got everything we need. So for this project, we needed our CL over CD, which is this first graph. And it's really cool because if in XFLR5, if you hit the numbers on your keypad, if you hit 1, it pulls up the first graph in the sequence. And you can do the same for each of the graphs. We can go 2, 3, 4, and 5 for the 5 graphs that it generated there. And then if we hit A on the keyboard, it takes us back to this view with all of the graphs. That's super nice. So you can see we have our CL over CD. That's one of the graphs we need. And then we have our CL over alpha, which is another graph that we need. And then we have CL over CD versus alpha, and that's the third graph that we need. So if we need to export these, because basically what we want to do is we want to plot the airfoil and we also want to plot the 3 different wings that we're going to experiment with. So to get that data, we can actually get it in an Excel file by exporting this. So if we right click here and go to current graph, hover over that and then go to export graph. If I click that, and I don't think you can see this that pops up, maybe you can, but there will be a pop-up basically that will ask you, to name it. It just comes up with like polar graph, and asks you to put that in there, and you can save it to whatever file you want. But yeah, it saves as a CSV file, but you'll be able to open it up just fine. It'll be perfectly compatible in Excel. If I actually go ahead and open up, I'll show you one of the ones. You can see all the ones if you see my screen there. You could see the ones that I've already saved for this project because I've already ran this, obviously. But if I pull up one of my ones for an airfoil and share that, you guys will be able to see what it looks like. I've adjusted it, so I guess this isn't a perfectly accurate explanation of what it looks like because I've actually compiled some of these. Basically, it'll just have 2 columns. The one that says CD, the other one has like some random characters that it's saved in from like what type of analysis you did and like the Reynolds number and whatnot. But it's just going to come up with this where it's got your, your CD and then your CL values. You should be able to figure out which one it is based on which one you saved, because it just saved it for the current graph. So don't worry too much about that, but that's basically how that will go. And then you can take all your data and save it into one file, which is eventually what I'll show you after we finish all of this in XFLR5. So that's how we do the airfoil, super simple. And then obviously when you export all the points to Excel, you can get all the data that you need and plot all the graphs that you want. But to do the wing, we're going to need to do a couple of other things. So the first thing we're going to do while we're still in this analysis spot is we're going to do a batch analysis. And basically what this is going to let us do is let us refine all the values that we get around the Reynolds number that we're going to be looking at, to hopefully give us the most accurate answers when we go to analyze the wing. So what we're going to do is, obviously our Reynolds number is 1 million. So we're going to do a range batch analysis. We're going to go from a range of Reynolds numbers across the alpha sequence that we set. So you can see we've got the alpha already set -5, 20, with an increment of 1 degrees. And then I'm going to do a min and max of Reynolds number of 900,000 and 1.1 million. So right, basically ceiling around 1 million and just an increment of 10,000. I'm going to take this iterations. I played around with doing more iterations earlier, but 100 max iterations should be fine. And we'll go ahead and do this batch analysis, hit analyze. So what you're going to see, ideally, this gets all the points to converge so that, again, we get the best solution when we get to doing the wing analysis. But that's probably not going to happen. I can see some have already not converged, and it says it on there, which is a little bit of an issue, but this is the best that we can do. I've played around with this a lot, and unfortunately, this is kind of the best that I've got right now. So we will make do with that. But that basically sets us up to design our wing. So we're going to hit File and go to Wing and Plane Design. It's going to pull up this nice screen here. And once we are here, what we can do is we're going to need to define a plane. So we're going to go to Plane and define a new plane. Name it whatever you want, doesn't really matter. I'm just going to name it Project. And obviously it gives you a lot of nice options where you can add a biplane, elevator, fin. You can design this plane, and it'll show you what it looks like in a second, but we are not worried about that for this project. We are just looking at the wing. So what we need to do is define the main wing. So we're going to hit define here, and it pulls up this nice little window over here that you should be able to see, I hope. But yeah, so we'll come here, and what we can do is we can adjust the wing here. So basically we can change all of these parameters that we want. So for this project, I just chose a chord length of 0.5. We could kind of pick the chord length and wingspan just to match the aspect ratio that we wanted. So we were kind of had free reign over that. So I just chose a chord length of 0.5, and then to get the aspect ratio that we need, it's a straight rectangular wing. So the aspect ratio, which is normally wingspan squared over planform area, it simplifies to just wingspan over chord length. So again, you can see it like it goes from y equals 0 to 1. So this is just the distance in one direction, and then that's mirrored on the other direction, like in negative y. So when I do y equals 1 here, that means that we've got a wingspan of 2. So here we've got a wingspan of 2 over a chord length of 0.5. That gives us our aspect ratio of 0.4 that you can see over here, or of 4 that you can see over here. I'm going to change this offset to 0 because we just want a normal straight rectangular wing. Dihedral and twist, we are not going to worry about for this. And then the last thing you need to do is make sure you click over here to give it the foil, because you can see it's just a flat plane right now. But once we do this, there you go. You can see that nice little foil that's been added, and it's actually created the wing here, which is exactly what we want. So for this project, we need to do an aspect ratio of 4, 8, and 12. So we'll do 3 different wings. You can just adjust this plane and edit it for each one. So what I did is I kept the chord length the same for each one, and then I increased y to 2 and 3 for aspect ratios of 8 and 12 respectively. So once we have this, we can go ahead and hit save. And then everything should be defined for our plane. So we go ahead and hit save with that. And you can see it pops up with all of our information here for the data on that wing. And then the last thing we need to do is we need to define an analysis. So we go to analysis and then define an analysis. And we're going to do a fixed speed analysis. We need to get the Reynolds number that we're looking for. So you can see it automatically popped up with 10 meters per second, and that gives us 333,000. So the proper speed that we need for our Reynolds number is 30 meters per second. And we're doing a lifting line theory analysis method. So we keep that the same. Everything else is good. You can see now our Reynolds number is up to 1 million, which is what we want. So we go ahead and hit save. And now again, this plane analysis has gone, it was grayed out, now it is not, now that we've defined our analysis. So we have our alpha sequence. Again, this is the same sequence we were doing before. So that's what we want to go ahead and do. So we will hit analyze and let this go ahead and run. Some of the points did not converge, but that's okay. Like I said, it's a little hard to get all of that to work perfectly. But if I go to our polar graphs here, hit all, there we go. We have all of our graphs that we were looking for. Super, super great. So again, same thing as before, you can hit the numbers to get the specific on your keyboard to get the specific graphs that you're looking at. And then when you're on a current graph, like if we're on the drag polar, the CDC over CL graph, we can again right click current graph and export the graph to get it into an Excel file, which is great. I was going to show you as well what the wing design looks like. This panel here is really cool for showing you all the different data. You can check off what you want it to show. So you can see we have like our induced drag is that yellow, viscous drag is in that purple. We have our downwash velocity in the red, you can see it's pointing down, and we have our lift in the green pointing up, which is super cool. You can vary it for whatever. This is at -5 degrees, but you can vary the angle to whatever you want. So here's at 2 degrees, you can see how it shifts. Got all kinds of different drag, and it gives you the different distributions along the wingspan, which is super cool. You can even animate it to go through the alpha sequence itself, and that's exactly what it's doing. And you can see in the bottom corner here, it's like going through all the different angles. Now we're going back up. Angle of attack is increasing. You can see it starting to tilt up and change all your values. You're starting to get more drag, more lift, more downwash velocity, all of that fun stuff. You can see it really is scaled out, and then it goes back down through the sequence. So just a cool little animation that you can do just for your own interest. So yeah, basically from here, if we do the same thing, run it for aspect ratio of 8 and an aspect ratio of 12 and save all the graphs that we want, you'll get all the data that you want. The other data that we want is when we go over to this plot, we can get our induced angle and induced drag versus the wingspan. So you can see it goes from like -1 to 1 here. That was our y distance in each direction. And so what we can do is we can go to whatever angle we want. So for this project, we were asked for 7, angle of attack of 7. You can do any angle that you want, really. But that's the one that we're doing for this. So what you can do is the same thing as the other one. If you right click and then go to current graph, you can export the graph and get the data points again. The other thing you can do is define graph settings. This is how you change it for what parameter you're looking for. So right now we're induced angle versus the Y-span. The other one, like I said, for the project that we're looking for is the induced drag coefficient versus the Y-span. And that's what it looks like. So again, you can export that, do that for each of the 3 wings. You're not going to be able to do this for the airfoil, obviously, because it has essentially an infinite wingspan. So you're not getting a distribution for that. That's specific to this case. That's basically what we're trying to do. And so once we finish this, this basically takes care of us in XFLR5. So I will show you what all of the data kind of comes out to look like when you get it into your Excel file. So this is what my Excel file looks like. Again, it took me opening up all the different files from each graph and kind of combining them into one spreadsheet. And then I just created sheets for each of the different types of plots that we were looking for, and then just put all the data into here. So that's, that's what I have. And then I was able to just plot it like this. I was just able to do like insert and then do a scatter plot with smooth lines, so that it connected all the data points, and then just added a series for each of these. So I was able to add a series for this, add a series for this, and so on, so that I have all the different ones. So you can see everything comes out like we expect. You have the airfoil with the greatest lift curve slope, which is super good to see. And then it kind of, the slope increases as aspect ratio increases. So that follows the pattern that we're looking for there for CL versus alpha. You have your CL over CD again. Greatest by far, of course, is going to be for the airfoil. And then you have your others where it increases with aspect ratio. And then our CD versus CL, you got this plot as well. And you can actually interpolate and get your zero lift drag coefficient from this. So you can look at the value where, like in this case here, you can see where lift transitions from negative to positive. So somewhere in there is where your zero lift coefficient is going to be. And you can interpolate between these 2 values to get your drag. So that's what I've got here, is I did that for each of the different ones based off of that. So that's super good. And then we also have like our local induced drag over the span and our local induced angle of attack over the span plots here. And so you can see, each of them, obviously we had to vary the wingspan for each of those. So that's why they're going from like -1 to 1 and then -2 to 2, -3 to 3. Could also have changed this for probably a better way to do this would have been to do just varying the chord length. And so that we would have had and just kept the span the same. Probably would have been a better way to compare these, but it does the job. It's still the same. Gives us an idea of representation of that, of basically what that induced drag or induced angle of attack how they're gonna vary. So it's basically the same for each one. It's just slight differences. But yeah, that pretty much takes care of us for the project. That should be just about everything that you need. You can calculate some of the stuff like downwash velocity and whatnot from the data points that you can get. But that should be just about everything for us. So hopefully this video helps and takes care of you for using XFLR5 for the project.